Okay, after the setup in the previous video, let's do some integrals in MATLAB. Let's start with the symbolic functions. I'm going to go ahead and type in, whoops, how about that? There we go. I'm going to type in sims x and f, all right? X, the variables x and f will be symbolic variables now. There you can see them over here. They're one by one matrices technically, but they're symbolic variables. And I'm going to say that f is that same function that was on the board. It's just like that. Hit return, there it is. And so I want to take the derivative of f now. Just type in differential, hit return, and there it is. Not short, but not very hard. Now let's try the opposite. Oops, there we go. Let's try the integral of f. Let's see what we get. Ooh, well, there is an answer. Very long, but it's got some stuff in it. What is cosint? Well, that's something called the cosine integral function. And that is itself an integral where the upper bound is where the upper bound goes to infinity. So it's a semi-infinite integral. There's no closed form solution for that. You have to evaluate that numerically, and it's not even real. So, yeah, I mean, I guess technically there is an integral for it, but boy, it's not pretty. And it's not something you're really going to be able to push around very easily when you're doing calculations. So that serves to make the point that the derivative of this function is not very hard. The integral is, you know, unless you're willing to go to fairly heroic length, is functionally just not worth doing. Functionally, for most students, it would be impossible. And that's pretty typical. Integrals, because they are inverse problems, are much more difficult than derivatives. Well, they're much more difficult to do symbolically. Now, numerically, they're not very hard at all. All right, let me go ahead and clear the screen. I'm going to clear the memory and then clear the command window. And let's try this numerically. Let's try that exact same function. So let's go ahead and type that function in as an anonymous function and make a plot. See what we're dealing with here. Now, I can leave that as it is, but it's going to complain when I try to work with this because I have that same problem we've talked about before, that I'm multiplying vectors and I'm not really saying how I'm doing it. So I'm going to put a dot there, and a dot there, and now it'll be happy. So there it is, and let's say f plot, and I'll use f, and I don't really know where to plot this. Let's go from 1 to 10 and see what this looks like. And maybe we'll turn on the grid while we're at it here. Now, as always, it comes up in outside the screen capture area, but there it is. I can clean that up a little bit, make it brighter. Let's make that bright blue, and let's double the line width, go from 0.5 to 1. So there, it's pretty easy to see, and I'll just check there. There we go. So that's what it looks like. All right. The x-axis is right there, so it's well defined, it's easy to draw. Finding the integral of this numerically shouldn't be too hard. Let's go ahead and find the integral from 0 to 10. And let's start by just using simple boxes. We'll just go ahead and do this Riemann sum. We're going to do this all numerically, and I don't necessarily need to do this as an anonymous function. I guess we could, but let's go ahead and clear this out. Again, I'll clear the workspace and clear the command window. And let's define, well, let's start by defining a dx. Let's maybe call it 0.1. Yeah, let's make it half. Don't need to see that. So x equals 0. Step by dx and go to 10. And f, I'm going to cheat here. I had that as an anonymous function. Let's go ahead and just do this. Now, so let's check and make sure we've got this correct and see what it looks like. I'm going to plot the two vectors, x and y. So here, f, x, and f. And as before, turn the grid on, see what we get. Okay, a little blocky, a little chunky, okay, but clearly the same function. Now, what am I going to get for a numerical answer? Well, how am I going to do this? How about I'll call this area equals, and what I have to do is sum all the boxes up, the height of all those boxes, times the width of the boxes. Now I'm going to have to decide, let me pull this back up here. I have to decide whether I want to base the height of each of my boxes that I'm going to sum up on the left or right hand side of each box. I'm going to go on the left. So I've got 1, 2, 3, 4, 5, I've got 21 values here, but I'm only going to have 20 boxes because each box has a point on the left and right hand side. If I'm going to start at the left hand side of each box, I'm going to sum from 1 to 20. So I can say area equals sum. I'm going to go end minus 1. That'll be 1 to 20 since we have 21 boxes. Now this is not going to be the right answer because I'm summing the heights, but I haven't multiplied by the widths yet. So now I'll get the right answer. Now I'm summing first and then multiplying by dx because that's the same thing as saying y1 times dx plus y2 times dx plus y3 times dx, and so on. I can just say y1 plus y2 plus y3 and then take the whole sum and multiply it by dx. So I really do want this number, so I'll pull that out. 0.6764. Is that right? I don't know. What would happen if we made dx smaller? So I've cleared everything out. Let's try this again. Let's say dx is something smaller now. Let's go back to 0.1, which is what I originally suggested. I have to recalculate x, don't I? There's that. Good. F. So now instead of 21, I have 101. And 6672, so slightly different answer. Well, we did it once, let's do it again. Let's make this 01. Now I have 1,001 points. Recalculate F. And do it again. 6648. So you notice the change is getting smaller and smaller and smaller. Well, this is what you'd expect. As the box width decreases, you should get closer and closer to the exact answer. Let's skip all the middle steps. Let's just make the box length width just crazy small. Let's do something nuts here. There. I've got 1,000,001 boxes now. That's bonkers. Well, let's just see what we get. .6645. So you can see the difference between 6648 and 6645. That's pretty small, and that was making the delta x, the box width, several orders of magnitude smaller. So you can see that we're converging on a solution as dx gets smaller, and that's what's supposed to happen. If I made this even smaller, this wouldn't change very much. So that's summing boxes using sort of a Riemann sum, just the most simple-minded way to find an integral. There's another thing called the trapezoidal rule. Let's try that. I'm going to clear all this stuff out now. Everything is still in the command window, so I can pull it up as I need it. Now let's make this not nuts anymore. Let's go to 0.5. Now we know the right answer is 0.6645. Let's take that. Calculate new x's. Now we're back to 21 of them. There. Calculate that. Now there's a function called trapz, T-R-A-P-Z, T-R-A-P-Z, trapezoidal numerical integration. So I'm going to pull this over here so you can see what it looks like. All right. So if I type in trapz xy, I'm going to get the approximate integral. All right. Let's try that. Sorry, xf. There we go. That looks better. What do I get? 6629. All right. Well, let's do the same kind of thing we did before. And we know the right answer is 6645, I think. Let's go to point 1. Yeah, I got to recalculate f. There we go. Now everything adds up. So I've got the same length in both of those vectors. Wow, look at that. I got 6645 with 101 points. That's a better answer. That's a much better answer. And the reason is because I treated those boxes like trapezoids rather than just flat top boxes. Now, I did mention before that I thought there might be a Simpson's rule built into MATLAB. Alas, I can't find one. Now, there's a bunch of them posted on MATLAB answers, so it's very simple to find scripts that people have posted to implement Simpson's rule. Now, there are more sophisticated ways of integration. If you look up a topic called quadrature, Q-U-A-D, it's the beginning letters, quadrature, that's kind of the more sophisticated way to express integrals numerically. And there are some very sophisticated methods out there. Now, unless you're absolutely adamant that your code has to run efficiently, quadrature is probably a lot of tool for the job. For most of us, trapezoidal rule will do the job nicely. So since this is a review, I'm going to stop there. I hope this helps. We'll talk to you next time.